what it is. Yeah. So let's see. Yeah, so we'll call this tunneling through Earth, right? Let me just, so what I mean by that, how many L's in tunneling? Double L or single L? I'm not sure. I think double L, maybe. Through Earth in 42 minutes. It's interesting, the word 42, the number 42 comes up there. It is like there is a, what do you call it, a sort of a joke in the academic circle that what is the answer to life and the universe, and like the biggest question you can ask, right? And the answer turns out to be 42. And the joke is that, I mean, it's about a story written by, I don't remember the name of the author. So in that, basically, they build the best computer, and it takes for many, many years, like I think it's in millions of years, they work on, the computer works on it, and eventually it spits out a number, just one number, 42, right? So that's all. So it doesn't mean anything, just a number 42. So that's kind of a joke, but it turns out that whatever I'm going to do today, the answer comes out to be 42 minutes. Of course, it is not as fundamental as that joke, because it comes out in units, right? In 42 minutes within two significant digits. So in a sense, but anyway, that's a reference to that 42 there. So what do I mean by tunneling through Earth? So we have, let's say that's Earth, right? And let's say we dig a hole, right? Passing through the center of Earth. But as I will point out, it is not necessary to go through the center of Earth. First of all, is that even practical? No, it's not practical. What is the deepest we have gone, dug? Probably 10 kilometers. I mean, not even that is, I think, exaggeration, probably few kilometers. That is all we have gone. And what's the radius of Earth? Just for reference, radius of Earth is 6,400 to two significant digits kilometers, right? And what we have done is probably in the last this digit, we have probably gone 5 kilometers or 10 kilometers. The deepest ocean is probably about 10 kilometers or something like of that order. So this is
12 kilometers, it is to be precise.
Yes,
12, it is 12 point some kilometers. That is Mariana Trench.
There you go. Yeah, so it's about 13 yeah, let's say 13 kilometers to two sig digits. So that's the deepest we can go. And there, if you reach, and then if you can dig, probably another 20 kilometers. We are nowhere close to this, right? So we are really on the surface. But hypothetically speaking, and another challenge is that Earth is like it is very solid on the outside. Deep inside, it's pretty hot, right? I mean, I think just because of the pressure, it gets very hard, and it is metallic at the center. It is metallic because we know that that's what causes the magnetic field rotation of the lava and so on. And even that is not very well understood. But whatever it is, we're pretending that this is solid Earth, right? Uniformly distributed. The mass is uniformly distributed inside the Earth. And in that hypothetical scenario, you're saying that you dig a tunnel, right? Is the question clear? Okay, or at least the phrasing of this. Okay. Yes. And then you say that, okay, then you stand here and you don't do anything, you just jump into that tunnel. That's it. Okay. Now, nothing else needed. You just jump into the tunnel. And the idea is that the moment you jump into the tunnel, you get attracted towards the center of Earth, right? like Earth is still pulling you, and it is getting attracted. And by the time, so you will go faster and faster as you go into the tunnel. And by the time you reach the center, you're going so fast that you won't be able to stop very easily. So you will keep going. So you'll keep going through the center of Earth because you're too fast at that point. And then you will go all the way till here. And it turns out that if there was no friction, it is like a oscillation or a pendulum or a anything that hangs and oscillates one way to the other. And then you ask how much time does it take, right? So the time period will be go here and then come back. So the interesting question is, what is t by 2? Right? What is that comes out to be? And that comes out to be exactly 42 minutes. To 2 sig digits, it's exactly 42 minutes. And just for reference, the mass of Earth plays an important role in this. It is about, to 2 significant digit, it is 6.0 into 10 raised to 24 kgs. That's a huge, like we are about 60 kgs, right? Just one order, and this is 24. So that's not surprising. That's very heavy, and that's the result, if you want. And I can sort of motivate that today. I can do that in various ways. How much? I mean, if you go in a lot of detail, there are a lot of questions you can ask. But very broadly speaking, that's what I'm trying to say. Any questions on this right away?
No.
Okay, is a statement of the problem very clear?
Yes.
Venkat, questions?
Yeah. Clear.
Okay. So if that is the case, then you would, so just to make it more dramatic, right? Just to make it more realistic, let's say, you would say that, oh, that's impossible. I'm not even interested in the problem. You can keep it. And anyway, I'm going to work on this. But it can be made more interesting in the following sense. You would say that, okay, this is very hard to dig, but what if it was Earth like this, and let's say this is somewhere here is London, right? And somewhere it's not in the same longitude, but somewhere here there is New York. Right? So that's New York. Right. We have some logging in. It's Prachi. Okay. So that is London and there is New York, and then the digging still not really easy to dig. It goes pretty deep, but then you don't at least have to go to the center of the Earth, right? So you're reasonably close on that surface, but still nowhere close to what we can really do. But you can do that, and then you can again say that, okay, you jump in. And when you jump in, you would say that, oh, will you move at all or not? Yes, you will move because the force is towards the center, and partially there is a component of the force that pushes you in. Like force is always towards the center, but since there is this tunnel is blocking you, you will tend to slope. It's like a slide, right? You will slide through, and again, right at the center of this tunnel, you will be going so fast that you will not be able to stop, and you reach all the way there. And then you can again ask, how much time does it take to do that? Again, remarkably, it's the same 42 minutes to 2 sig digits, right? Same number comes out. So in fact, you can connect a tunnel from anywhere to anywhere in this on Earth, and always it is 42 minutes. And that itself should be interesting, that, oh, how come it comes out to be exactly 42 minutes. And that's what I'm going to show very. I'll make it simplistic. I'll use some statements instead of proving that. It depends on who is listening, then I can make it as detailed as possible. So that makes it a little more interesting, but that is, again, I should say that it doesn't make it feasible. It is not possible to even dig that kind of tunnel. It's really deep and we are nowhere close to that. Okay, so that's the statement. So how do we go about is working on that. So we first accept that there is, if you have any two masses, let's say two objects, let's say, let's keep it spherical, let's make it simple. So let's say there is Earth, right? So that's the mass of Earth. So let me keep it capital M, and just for making it very clear, I'll say a small subscript 1, and there is another object here, M2, let's say small m, relatively it's a smaller mass. This could be the satellite, that's the Earth. And it turns out the force acting on this, that's what Newton taught us, the force acting on this is first of all, it is inward. So force has two ideas in it. One is that it has a direction, and then it has a magnitude. The direction is got by, this doesn't have to be a point object, start from the center and go to the center. So, and then it is attractive, so it is minus r hat. So what does the symbol mean? This symbol just means that along the line joining it, it is towards the center, and that minus is included in that. So it's minus r hat, just means that it is attractive, it attracts towards the center of Earth. And it also depends on a constant g, m1, m2 over the distance square. Okay, so that's a bit of mathematics, but the simple idea is that it depends on the masses. If you're heavier, the gravitational force is larger. If you are heavier, the gravitational force is larger. If Earth was, if for example, if you were in Jupiter, the force will be larger. But it also depends on the radius, how far you are. So if you're in Jupiter, its mass is larger, but then its radius, if you're on the surface of Jupiter, that's also very large, and it's in the denominator. So whenever something is in the denominator, it weakens the effect. So the force weakens in a Jupiter also, and it is a square of that. So effectively, even though Jupiter is about 1,000 times larger in mass, because of its radius effect, together it is not that you get crushed on Jupiter. It's about 3 times larger. The acceleration due to gravity, what you feel on the surface of Jupiter will be about 3 times more than Earth. So it's not like it is 1,000 times or so, and that's because of the denominator effect that the radius is. So that's your force. Okay, and that is the reason for whatever I'm going to tell you. And this is very easy to realize, and this is what we study in textbooks. But I'm going to say that it is slightly different when you're inside Earth. Okay, like if you're already familiar with this, that's perfectly fine. Gravity gets weaker as you go farther, right? But if you already notice there is a challenge, this probably cannot be true in the inside the Earth, because right at the center of Earth, it would think you would, if you go by this naive expression, that is this r going to 0, which might really make it 1 over 0. It is 1 over infinity, or it's an infinite quantity, and maybe that's not well defined. But there is also a surprising part in this, that is this has a radius r, correct? Earth's radius r. This expression does not have the radius r in it. Okay. Is that, and that's just surprising, or that should be interesting to realize, because what that means is that sitting here, so for example, if you were on the satellite and you made some experimental measurement of gravity, you cannot measure the radius of Earth just by sitting on a satellite. You can actually visually do it using techniques, optics and so on, because you have a background and you might do that. But you cannot measure the radius of Earth by gravitational force measurements alone, because gravitational force on a mass outside Earth does not have the radius r in it. And this is true even for smaller particles like electron and proton. And that becomes a challenge because you would really like to know what is the radius of a proton or radius of an electron. And we cannot really touch it because it's so small, but we can actually feel the effect of it. Like atomic forces are measurable. But what that means is that by making any measurement, in that case, it is electric measurements, you cannot really measure the radius of the proton because that doesn't have the information of that radius of the electron. The only way to do that is to actually dig into it. Right? You have to go through the Earth to be able to measure. So you cannot just measure gravity outside and get the radius of Earth. So that's all features of gravity outside the surface of Earth. And we are typically on the surface. So you have to replace this R with capital R. Right? Till now, clear? Any questions? The only thing I'm pointing out is that if you're outside, it is R independent. So it's radius independent, R independent. Like that's non-trivial in the sense that the way you would convey that is that can you design an experiment where you measure gravity and measure the radius of these other questions here. So you say that, okay.
Basically, it is just saying that, I mean, you do not care about the shape of the object. You only worry about where the total mass of the object is actually considered located and measure the distance from that point to the other object. So, I mean, ideally it is considered like, I mean, I think the picture is just a point particle, right? Like all the mass is considered to be located at one location without worrying about the distribution, how the mass is distributed around.
Correct. I think, yes, the statement is that you can replace this whole mass and replace it with a point object, and there is no difference. The effect, as far as effect goes, there is no difference in the effect. Yes, that's correct. Yeah, and that is exactly the question you would ask. For example, we know that Earth has. Yeah, exactly. That's an interesting point you're making. That we know that Earth has a lot of metallic structure in between here, right? You would like to know what is that radius, right? Let's say this is R1 and that's R2. A very reasonable question would be that design an experiment, and the only condition I put is that that experiment can measure only gravity. You cannot do any other measurement. So doing gravity measurements alone, can you measure the radius R1? That's a very reasonable question to ask, and we would be interested in that because that has effects, right? We would like to know what is the structure of Earth like. And we cannot do that using gravitational fields alone. But that doesn't mean that we cannot really do that. We can do that. I mean, just for completeness, I should say, how it is really done is that you use sound. Like, for example, whenever there is an earthquake, it sends vibrations. And now this is not gravity, remember, when there are sound or vibrational waves going through Earth, that is not a gravitational force, it's just a matter wave going through. Using that, you can say, so there is a wave that goes through, and that involves two speeds. There are two modes to that motion or the sound wave, and one of them goes slower and the other one goes faster. And the rate at which it reaches here, the two waves, the difference between the speeds can tell you something about how much is the density of the material in between. So that is roughly how it is, very hand-wavingly. That is how you measure the radius of Earth. And it is reasonably well understood. It is understood that it's a lot more denser in the inside and less denser outside. And if we take care of that, the result of 42 changes a little bit, but we won't talk about that too much here. I'll just mention that, yeah, if what I'm assuming is that Earth is uniformly mass is uniformly distributed. If you take care of this realistic part of Earth's mass distribution, the result that the time period is 42, it slows, or actually you take less time, because it is attracting a lot for a longer duration of time. It takes only about 38 minutes to reach that in that case. Okay, yeah, good point. So that helps. Any questions at this stage before I proceed further?
No question. Okay.
Okay, great. So I said this is all outside, right? And I said this is our independent. What happens inside, right? We would like to know what happens inside. So outside is our independent. So let me say, yeah, our independent, and this is outside. That's it. And the inside, let me write down the result. I will motivate this in a minute why this is the case. It turns out, so notice that as you go farther and farther, it gets weaker and weaker in as far as gravity goes, as when you're outside. When you're inside, that's not the case. This becomes Gm1, m2 over, there is a radius of Earth comes out, so that's Q. And the R itself, how far you are, that's on the numerator, right? The expression for the force changes when you're inside. And why is that? How do you motivate that? One is, of course, you can prove that that is actually the case. So to motivate that, what I say is that, so first let's imagine a planet like this. So this is a hypothetical planet whose mass is completely distributed on the surface, right? So this is a shell, right? So this is empty inside. I don't know if such a planet exists or not, but you can imagine hypothetically that such a planet exists, and all the mass is distributed on the outer surface. Okay. And then you ask this, again, the interesting question that now it's easy to dig, right? It's an infinitely thin shell. If you scratch it, you are inside, right? And you make a hole there, and you again jump in, right? And you jump in, and then you ask, so now you're here somewhere. The question one will ask, curiosity, is that now what is the gravitational force? There is no mass inside. Do you get attracted towards the center, or do you get attracted towards the surface? Like surface is so close, one would think that surface might pull it. Like you're very close to the surface, that might dominate the effect completely. And sometimes you will argue that, oh no, like you can split this here. There is a force from this point, there is a force from that point, and that all balances. So it's not very obvious to answer that question. It is, or using simple arguments, it is not easy to convince that what is the actual force? Does it get attracted towards the surface or towards the center? And the answer is even weirder, if you want. The force is zero. If you are inside a shell like that. Is that any questions there? It should surprise. And I can motivate this a little more, but without mathematics, it will be a little harder. Yeah.
I just wanted to know if a person jumps, so will he get attracted towards this thing, or when when he comes out, how he will come out? Because as I was saying last time also, that because when gravitational force is acting, actually everything should fall. So how it will be even if the force is very if he jumps into that hole, with what force like
if you just, for example, float, right? If you just stand there, and because there is no floor, there is no, right on the surface, there is gravity acting down, right?
Okay.
And or you can say that from here, right? You jump in, right? There is a swimming pool like structure here, so you jump in there, right? Until you reach here, it is normal gravity, normal Earth, right? So you have a lot of velocity here, right? You're going with a large velocity at that point. It's like jumping into a swimming pool, right?
Okay.
But then you remove the surface, right? It's like having a table sitting there. You just move the surface. Oops, there is a lot of velocity there. You will just go in, right?
Okay.
But remarkably, the moment you go in, there is no force. But that doesn't mean that you will stop moving, right? You'll keep moving. In fact, you won't accelerate anymore, but you'll keep moving. And with that uniform velocity, you'll keep moving because there is no other force acting on it. Does that make sense?
Okay.
Like, it should not make sense in the sense that unless you get convinced that this is actually zero. And I'm not really convincing you, I'm telling it as a fact that that's what it is. And the only way I know how to do that
Is it some kind of geometric thing that it will always work out to be zero?
Yes, it depends on the fact that this is a sphere. If it was not spherical, for example, if this was having a dip, right? If the Earth had a small valley in here, right? So there is Mariana Trench, right? That is a big valley in there. Then this doesn't work, right? This perfect zero doesn't work. Right? That requires that it is really spherical. Even the fact that it is slightly elliptic, our Earth is slightly squeezed, very little bit, tiny bit. And within two significant digits, our Earth is really spherical. Like if you talk about Earth's radius within two significant digits, it is perfectly spherical. So it's only when you go into the third significant digit, it's really not really. So within 1% accuracy, that means our Earth is spherical. And in that case, this works. But still, that I haven't told you why that is zero. I have to use mathematics, or at least I personally know to prove that only using the mathematics or using some theorems like Gauss's law. So otherwise, I don't know. I mean, as such, how to motivate. Once I accept this, then I can convince you why this is the case. From that point, I can convince you. But I have to first use a theorem if you want that if you have a shell, then inside that gravity is zero. And is it possible to use some physical arguments to get that? Is it, Prachi, do you know any arguments where you can physically argue that force is
I
zero?
don't think physical argument. I can only think of the symmetry arguments that,
Symmetry,
yeah, like
symmetry argument, at least in my view of looking at it, so this is how I look at it. So that there is this mass, so this is a weaker force here. The same thing here. These two can cancel out, and then there is a horizontal force there. And this is a little larger force. But still, why these two should cancel, that's not very obvious in the symmetry argument, right? Like, is the symmetry argument really prove it?
I mean, you drew a simplistic picture there, right? We know that there is infinite many.
Yeah. But you can keep adding it, and there will be a lot of forces, and this all has to add up to exactly the force coming from that, right? So what you're saying is that the force exerted by this part of the Earth is exactly equal to the force exerted by that part of the Earth, even though it is not at the center. So that symmetry really doesn't prove it, right? Or at least it's not fully true, yeah, but symmetry is necessary, I completely agree. So yeah, so Vipin, I will try to use this fact. Okay, so inside a empty Earth shell, right?
Okay.
Gravitational force is zero. Outside, it is normal, as if it is the normal Earth. As far as this is the same mass concentrated here, outside no difference because there is no radius r, remember, right?
So can it be
Uh-huh.
can it be like individual if a individual like jump? So can he float in at the center because there is no gravitational force?
Yes, you can float. Yes,
Okay.
exactly. So if you, I mean, what we usually say is that,
Actually, that is not what it will do. He's not going to float. If he, whichever direction he is going, he'll continue going and hit the other side.
yeah, but that's floating, right?
That not exactly floating, right? It's he. If he gonna hit, then it is collision, right? And then
No, what
whether
I'm
he's
saying
bound.
is when you're going here, you're just gliding, right?
Yeah, but
There's no acceleration.
gliding doesn't mean that you have stopped there.
Yeah, so floating, yeah, floating means you're just moving, but you won't be able to stop because there is no friction.
I
Right?
was what I meant was, will he stop there, or will he continue to move?
He will continue to move and hit the
Continue
other
to move.
side,
Oh, okay.
and
If
then
we have
there will
some
be
air
probably
here,
bouncing.
so let's make it better. We will put some air inside so that we have some, what is that called? Sailboat kind of system, so we can use the
No, air inside doesn't work. I don't think you will mess up. Like air is mass still, so don't
Let's say
bring in
mass was there. I mean, to two significant digit air doesn't have mass,
Okay.
right? To two significant digits air doesn't have mass.
Okay.
So in that sense, again, remember all this is idealized, but yes, so the point is, yes, we can go around there and even stop to a certain extent with those effects. And I think the best way to say it is that if you like to clarify that this is zero, the gravitational force is zero, you take a weighing scale, we stand on a weighing scale to measure our weight, right? So if you were to stand on a weighing scale here, you will measure your normal weight. And the moment you cross the surface, it will become zero. You won't weigh anything.
Okay.
Right? Your weight will become zero. So that's a good way of pointing out what that is. Right? Does that help a little bit?
Yeah.
Okay, so if we, so now what I have told you is that, so that is the case, and then now I have a shell, so this is shell, right? But of the same mass, and again the same M2 here, right? M1 here, and in this case the force is minus R hat G M1 M2 over R squared, and this is zero. Outside, and this is inside. Okay, and just for completeness, it depends on whom you want to convince. I just made a statement. This can be proved that this is equal to zero. So what you typically do is that you break this into small pieces, and you keep this mass here, and you basically integrate. Right? So that's not, and that integration is not very hard. Like it can be done at a high school level integration. You can actually prove that that's equal to zero. You just have to make a choice, a judicial choice as to the observer point should be somewhere along, or choose it along the z-axis, and then that works out well, right? So, so my point is that, yeah, you can prove that that's equal to zero. Okay, so if that is the case, now next thing we say is that we now come back to this point, but now we say this is uniform mass there. So now it is back to this, right? So this is like full, this is a solid earth, right? So this is shell, and that's solid. By solid and shell is that all the mass is on the surface. This is uniformly distributed. This time, let's just have an abstract point here, just for our reference. Right, that's my radius R. Right, that's my observation point. I would like to measure my gravitational force somewhere inside. That's at distance R, and let's say the radius of Earth is R. Right, so it's somewhere inside. So this observation point, you're standing here, and you stand on a weighing scale, and you want to measure your weight and how much do you weigh. Now it is easier to do this calculation, because now you argue, because of this result, anything outside this dotted line that I have drawn does not affect you, because that is, you're inside this, right? You can break this into many rings or shells, and once you go each shell inside, gravity is not pulling it. So your gravitational force is effectively decided by this radius r. So we just have to know what is your mass, the mass of this dotted surface. If it is uniformly distributed, we know that density is the same. So mass over 4 pi by 3 r cube, right? That's the density. That's a total mass divided by the total volume, has to be equal to the mass inside this dotted surface. So let me call that m prime over the new volume, which is a small r cube. That allows me to calculate what is the m prime. That means it's not the whole Earth that is pulling you while you're here. It is only that part of the Earth which is inside you, right? Inside in the sense, from the center to this. Anything outside cancels out because of this effect, right? Because you're inside of that shell. You're breaking the Earth into many shells. And while once you cross that shell inside, that is not pulling you anymore. So the effective mass that pulls you is, so basically you're reducing Earth's effective mass as you go inside. The 4 pi by 3 cancels, so it is r cube over r cube times m. Right, so that's your effect, right? That mass is actually the mass that is pulling you is reducing as you go inside. In fact, at the very center, your force will be 0 because this has gone down to 0. The mass, effective mass that is pulling you is 0, even though you're at right center. So let's pull this all together. So there is so the force inside would be G. Now that is m prime now is r cube over r cube times the m. That's your mass that is pulling you, and this is m2, that's already there, and divided by r square. Right, that's your old r square. So there is a scaling effect of r cube because of the mass. Like, since you're getting closer, there is less mass in there. So that gets scaled by r cube, and there's r square just because our gravity is there, and that is, again, it is a surface area that is coming in there. These two cancel out, and this gives you this result, right? So this is equal to G m, so this is m1, m2 over r cube times r. That's inside. Outside, it's the same. So that's the way you motivate that. Was that clear, Bipan, the argument that once you're on a shell, it is not there, so break this into many shells. This doesn't pull you, it's only that part that is pulling you. Does that help?
Yeah.
Okay, so the take-home part is that it is linear. When you're outside, radius is in the denominator. That means you go farther, larger distances makes it weaker. But if you're inside, larger distances actually makes the gravity stronger. So your weight will be larger when you're on the surface, and you will go lighter and lighter as you go center. So if you go very slow, so if you hold on to the wall of the tunnel, don't jump in. If you hold on to the wall of the tunnel, then you will weigh more here, and then you will weigh lighter, 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 and eventually here, when you reach the center and you weigh yourself, you will be exactly 0, right? So that's the opposite. If you go down up there, you get lighter. If you go in also, you get lighter. In this case, you get lighter immediately, but in this case, you will go lighter and lighter slowly, and then you will reach 0. That's your effect. I mean, and that's what we need to now point out why that time period comes in. So let me go to the next board, come back here. So what we have at this point is that inside, so this is now inside, we have shown that gravitational force is slightly different, and its force is not worrying about the direction, it is always inward, and this is the negative sign still tells us it's inward, and there is a constant, right? So there is Gm. This is all decided by Earth or the planet we are in. If you are on Jupiter, the mass changes, the radius changes, but this whole thing, once if you say that you're going to sit on one planet and not worry about other planets, this is all one number, right? And this is R, how far you're from the center. This is always inside, okay, right? You're sticking to inside. So there is a force which is linearly proportional. So that means at zero, right at the center, its force is zero. As you go farther, its force increases. So it is like saying that you're here, and this is the center. So that's your Earth's surface. If you're right here, there is no force. If you're right at the center of the Earth, no force. If you try to move away from the center, it will pull you back. Right? If you go this side, it will pull you back. And that's like a rubber band. Like rubber band works exactly like that. If you have pull the spring, it will pull you back, right? So think of a spring now. So there is a spring, and you attach a mass m here, and you attach it here. If you were to pull it this side, it will pull you back. And that is also linear. So this is called a spring force. So this has this effect of a spring. If you're at the center, it is happy. If you go there, it will try to pull you back in a linear fashion, right? And the moment you have a spring, there is this oscillation effect, right? You can talk about this oscillates. It goes up and down, and you can talk about how much time does it take to go up and down. And that time is decided by this coefficient in front. Like anytime you have a force which depends with a negative sign on how far you're going, whatever is in front has the information about the time period. How much time does it take to go up and down? In fact, it will have the units of that quantity. So let's see what that is. So, so we will define this. So this is 4 pi square over the time period square. So how much time does it take to go, the spring takes to go up and down is decided by whatever is in front of that coefficient. Okay, so that's Gm over R cubed. So that's it. So again, what all did I use? I used the fact that a shell has zero force inside. Using that, I argued that the gravitational force is linear. That means to say it is zero inside, and it grows to a large value there, to 9.8 meters per second square for 1 kg of object there. And that is going linearly. And if that grows linearly, that is equivalent to a spring. If you leave something here, it oscillates here up and down, right? In fact, when you jump here, that 42 minutes, if you were to do nothing, so if you reach here, you have to pick him, like there should be some mechanism where you pick him. If you don't do that, you will again start going on the other side. So you'll keep oscillating unless someone comes and picks you from that point. And then the time period is just got by this, and let's calculate this for the planet Earth, right? So this is the mass of Earth, radius of Earth, and this is a gravitational constant. That's a universal constant here. So I have to get T, so I have to take the square root of this. So this is T is 2 pi times R cubed over Gm. And that is the square root of this. And this is equal to, let me try this. So I'll do two significant digits. So R is 6,400 kilometers. So that is 6.4. I have to work in meters. So that's 10 raised to 6 meters, right? So that's cube. Right? And I should also point out that this is in meters. Right, so this is meters cube. And then there is G comes out to be 6.7. That's a constant that Newton brought in, introduced, and that's 6.7 into 10 raised to minus 11. And this units for this is Newton meter square over kg square. There is no simple units for that. And the mass of Earth is two significant digits, 6.0 into 10 raised to 24 kg. That is 6.4 cube. There is 6.0 into 6.72. So 6.4 square is approximately the same as 6.7 into 6.0. That's just a observation. It's about 42 actually, 40 actually. Everything comes out to be around 40, it seems like. Yeah. It's actually off by small. This is 40.2 and this is actually 41. So within a 1%, it is exactly the same. So there is a 3 powers of 64 there. 2 of them cancel out. The powers is 10 raised to 18, 10 raised to 13, 10 raised to 5. Give one of them to 64, that makes it 8 squared is 64. So this is 2 pi times 8.0, and whatever is left out is 100. 10 raised to 2, there was a 10 raised to 5, one I gave it to 6.4. And that's what comes out. And this is in seconds. Like if all these units are cancelled, this comes out in seconds. So for minutes, I just divide it by 60. Right? And let's say so this is a time period. That means it's the time taken to start from here, go all the way across to the city, across the diameter, and then come back. So it's a one full swing. So if you're on a swing, it is keeping going full there. So it is T by T is what we are interested in. So that's pi, and this is 800 to 2 sig digits and divided by 60 to make it in minutes, right? And that comes out to be to 2 significant digits. It comes out exactly 42 minutes, and that's the result, right? So what are the things I used actually? I said that inside Earth, inside a shell, it is 0. Then I argued that it is linear in the distance. And then I compared it with a spring oscillation, like a swing, right? How much time it does take for the swing to go up and down. And using that analogy, I got the time period of the swing to be exactly 42. Pippin got disconnected. I was addressing it to Pippin. We'll give it a minute.
So is there an electrostatic analog to this problem?
Yes, there must be. Good question. You can make a charge. Yeah, I mean, it goes exactly identically actually, but yeah, it has to be a negative charge. If it is a positively charged sphere and there is a negative charge you introduce. Good question. I don't know. I mean, by analogy, yes. I mean, calculation will surely go through, no doubt. Okay.
But wouldn't I get radiation?
Oh, neglecting radiation.
Okay.
Like the electrostatics.
Okay, electrostatics. Yeah.
Statics, yeah. Good point. Actually, you should bring that in here also, right? So we are neglecting gravitational radiation or yeah, I mean, what if gravity, I don't know how it works because dipole doesn't radiate in gravity. So yeah, I don't know. It will be interesting to ask just as an academic exercise, how does this result change if you introduce the fact that this is actually radiating or gravitational radiation is coming out of this. It will be weak, of course, but you could ask what is that effect in a sense.
Yeah, it's always weak, right?
Yeah, of course. Yeah, very weak. But in the context of electrostatics, that becomes very reasonable and doable, probably. I don't know. I mean, yeah, I have never thought of that. I did not even think that what would be the analogous case in electrostatics. Like it's like saying that if you have a proton, like it's tiny, but proton, like let's say it's uniformly charge distributed and electron really penetrates through a tunnel. How much time will it take? Yeah, we can actually calculate that, right? Let's see. Let's calculate the time it takes for an electron to go through proton just for fun. Okay. Oh, Bipin is back. I'll come back at your question. Yeah.
Sure.
Bipin, did you miss things?
No, actually, there was some net problem.
Yeah. But were you there until I brought the 42 minutes, or did you get disconnected before? You got disconnected again, I guess. Hello? Yeah, I was just saying that I use a couple of results that for a shell, gravity is 0, then argue that gravitational force is linearly increasing, it acts like a spring, and then whenever you are in a swing, there is a time period well defined, and the time period in this case you calculate to be 42 minutes. For Earth, it's a very Earth-specific result. For Jupiter, it will be different. For Moon, it will be different. And yeah, so questions. Venkat, you have a question, so let's. I'll come back to that. Bipan, do you have questions? If you're there.
No, but one thing I just wanted to ask.
Yes.
Actually, you were mentioning about the earthquakes.
Yes.
Okay.
Yeah.
So
Yeah.
what? So when there is an earthquake, like, so it is like there's some gap between the two place of Earth, or is it like in case of tsunami? They say that there is undercurrents. And
Yeah. So let me try to say what I mean there. So for example, let us say if I had let's say if you have a pipe, right? That's a simple cylinder, and that is liquid, right? This is liquid. And let us say there is a diaphragm here, and I shake this, right? I bounce this and bring it back. So it starts moving, right? And then you ask, how much time does it take to reach that here?
Okay.
So T, let's say, how much time did that effect take to go from here to there? It takes some finite amount of time. It depends on how the vibrations move in that cylinder. Reasonable?
Okay.
Okay. Now it turns out that this vibrations has two modes. And they go at different speeds. So there are two effects like this. This sound, even though you made only one click, one of the clicks you will hear after, let's say, 2 seconds. Another click you will hear after, say, 1 second. So there is or 3 seconds. So let's say there is a lag in those. And those are same effect, but they're happening at one is slower and one is catching up. So there are two modes happening. It's like music. One of them goes at another, or you hear two times, let's say. Like you're listening to music in the radio, but there is some disturbance. So first you listen to it and then again you listen to it. Is that clear what I'm saying?
Yeah. Okay.
Now using that, this is a very simple cylinder. Now do this for a sphere. It gets complicated. This effect is still there. So you have to do that calculation in a slightly different way. So what you do is there is Earth here. It doesn't have to be across. You're somewhere here. Let us say you're in New Delhi, right? And there is an earthquake in Pakistan, and you're somewhere here, right? So this is somewhere Pakistan, and this distance it goes through Earth. And using the same effect, you can actually calculate how much time does it take, and based on how much time it takes, you can calculate this distance. In fact, you can also calculate what kind of fluid is in there. Like you can tell something about, oh, is this a very dense liquid or is it a very less dense, rare liquid? So those are the things you can do, and that requires a lot of experimentation. But roughly, you can talk about what it is made up of. Does that make sense?
Yes. Yes.
It is like saying that when you are in air using sound waves, you can tell what is there in the air, right? Even though we don't see it, just by listening to how much sound is coming from each direction, you can say, oh, there is an object there, there's an object there. Think of a blind man walking, right? So they use sound in a much better way than echogram, maybe that's what it is, echogram, that's what probably it's called, something like that. Yeah.
Just a comment.
Yeah.
It's in the seismology.
This should be seismology, I guess. Yeah.
Yeah. Even this in IIA Bangalore, they do it for sun and they call it helioseismology. Yeah.
Correct. Exactly.
Yeah.
I know that that's done for sun. Yeah. They try to understand the structure of sun using this. Again, the same challenge. See, we would like to know what is there inside sun, right? But we cannot use gravitational effects to understand that. Gravity does not talk about inside. Gravity only talks about outside. The only way to understand sun inside is to either penetrate inside the sun or do something else, like what you're saying, seismology. You cannot use gravity to understand the inside of the sun. You have to use some other effect. Typically, magnetic effects are used, or what you're saying, seismology is the best one, yeah, if you want to understand the model of sun. Yeah, good point, very good point. Yeah. Okay. Yeah, so Venkat, you asked a good point. So what if this was a proton, right? So let's say this is the same, instead of Earth, now we are inside a proton, very tiny. Radius of a proton is about 10 raised to minus 15 meters, right? I don't remember the, let's do an order of magnitude calculation. So that's what it is. And our force would be equal to, in that case, 1 over 4 pi epsilon naught, right? And there is a charge Q there, and there is R over R cube. So remove the R to get the time period square.
So you mean to write as electric field, not the force?
Yes, I meant to write the electric field. Yes.
Or write it as force per unit charge.
Yeah, electric field. Good point. Thank you. And it is an electron that this time is jumping into the proton. Okay. The electron is jumping into the proton, and see, or we shoot it right at the center, right? Can penetrate through. Okay, so that's T is equal to 2 pi times R cube, or 4 pi epsilon. I think I can put it to the denominator, right? We know that what it is. So R cube over K times Q. That's what it is. So that's equal to 2 pi times order of magnitude. So R is 10 raised to minus 15. So it's 10 raised to minus 15 cube divided by k, which is 9 into 10 raised to 9. So that's about 10 raised to 10 order of magnitude. And the charge is 10 raised to minus 19. Okay, so that's equal to 10 raised to minus 45. So minus 45, and denominator is 10 raised to minus 9. Right? So 45 minus 9 is 36. Isn't that h bar? Right? So 10 raised to minus 36. So that's about 6 into 10 raised to minus 18 seconds. Did I do that correct?
Yeah, seems like.
Yeah. So this has a E in it. Yeah, it's not that h bar. Yeah, it's not this. Will be the proton radius, not even the atomic radius. Yeah. So yeah, it's about 10 raised to minus 17 seconds order of magnitude. Yeah, I don't know what to make sense out of that. Like using h bar, can you construct time? So h bar omega is energy, right? So electrostatic energy of a proton and an electron, when it is atomic thing, is electron volt, right? But this is really heavy energy. And that energy probably divided by h bar. So yeah, omega, so T will be equal to 2 pi times h bar over E, I guess. Right. So it will be, yeah, so the time, so this time, whatever it is, should be the h bar divided by the energy of electron and a proton right at the surface. So that's what probably it will be. But yeah, I don't know what that is. Yeah. Not sure. Yeah, but good point. I never thought of this. It's like saying in a CERN experiment, I think there it is 2 protons coming and hitting each other. But suppose an electron and a proton are coming together and it really penetrates through and it has to go through it. What will it do? In a sense.
This is all classical, right?
It's what? Oh yeah.
This is all classical.
Yeah, it was pure electrostatics. Yeah.
Classic.
Yeah, classical electrostatic. And oh, you're asking, oh, where is the h bar coming in?
Coming from, yeah.
Yeah. So there is not even a mention of that. Yeah. True. Yeah. But then there is this E square over h bar, right? E square over h bar C, I think. Right. So that's approximately 1 over 137.
I guess that is just going too far. Like, let's just stop that discussion over there.
Yeah, I think we should stop there. Yeah. Okay. Agreed. Yeah. Okay. But it's good to ask, yeah, what is the can we think of some electrostatic analog of this in a more realistic sense? Maybe proton is not the good way to think of it. Let's say Van de Graaff generator, right? You can really build a charged shell there. And then you go into it to put it inside. It's a Faraday cage. Yeah, that's a Faraday cage, right? So, but there are other effects coming in. Conductor has different properties, right? Yeah. Or you can put it the opposite, like what is the analog of a conductor in gravity? Other materials, it doesn't polarize, right? There is no polarization. There is no negative mass. So yeah, good point. Yeah, that's all. For a change, we should stop at the right time. Yeah.
Nice.
Yeah. Thanks, Vipin. Yeah, you asked me this question, so that's what motivated me.
Yeah. Thanks for your efforts.
Good.
Efforts. I see.
Okay, nice.
I just want to make a comment. I didn't hear you making the connection with the satellite going around the surface of
yes,
the Earth.
yes.
Yeah.
I can do that. So yeah, that's a good point. Now this time, like this is 42 minutes or 84 minutes, you should say. That full time is T/2 is 42, right?
That is
And-
one thing. And another thing you didn't comment on, like which you have worked on, if the density, like if the mass is not uniformly distributed, that changes the time period a bit.
Yeah. So yeah, I can mention touch on both. First is now notice there is a time associated. This is 2 pi, or let's say t square, right? So this is gm over r cube, 1 over g of minus 1. Right? So that's gm over r cube minus half. Right? So that's anything that happens inside of the Earth, there is a time period that will use this time. Somehow this was a scale of time inside, anything that is happening in the inside of Earth. Outside Earth, that's not the case. It's different, right? But inside and outside, there is a boundary, right? And that is right at the surface. And if you imagine a satellite, so remember the satellite moves on its own, right? Once you put it in a target and it has a velocity, it moves on its own. It is just falling basically, right? It is falling up and down. But let's think of a satellite really hugging Earth. And then we ask the time period of a satellite or a planet going around sun, or a moon going, or a satellite going around Earth, is completely decided by the mass of the planet and how far the planet is. And in this case, this is simply got by mv square over r. So mv is omega square, right? So it is m omega, which will be 2 pi over t square times r. That's equal to gm over gmm over r square. That's it. And again, if you calculate this t, it comes out exactly this. Right, that you can see it almost here and cancels out, and then there's an r cube in there. That's exactly the same idea. One can ask, what is the similar thing that happens in, for example, a simple question would be, if you have Earth and you start from infinity and you jump in, or you fall starting from 0, how much time does it take to reach the surface of Earth? So that's also a very a time that sets a scale that turns out to be infinity. So that's the only catch. So somewhere you can say that you start from 2r, right? So you start from 2r and you reach r. How much time does it take? And that's not this t. Okay, so those are all good times. But the main point I'm trying to say is that outside Earth, the scale of time changes a little bit over inside. It's only a number, but it's the units wise, it will be exactly the same. So that's what Prachi was pointing out, that the satellite takes exactly the same amount of time. The second is we argued that, so if you have Earth now, it turns out that real Earth is little more denser here. So Earth can be simply modeled as a very dense part and very lighter part on the other side. And in fact, G, if so, let's compare the two, right? So this is uniform, and this is more dense here and then weaker in there. But both are mass m. Both have the same total mass. And if you were to have gravity measurements for this, it goes, we said it grows linearly high, right? Starts from 0, like you weigh 0 at the center of the Earth, then you keep increasing. That's your radius r. That's your g measurement. And then it decreases like 1 over r squared. that's how your weight will change. Your weight will keep increasing inside it until you reach the surface, and then you keep going down. If you do this in this scenario, so this is your R, and that's the maximum, so 9.8, right? So this is 9.8 meters per second square. Same thing here, 9.8 meters per second square. But let's say this is a good model is this is R by 2 for half the radius. It's exactly 10. So it is not, and that is what model says. So if you go half the radius, you reach gravity already. Right? So that's how it is dense enough that within half the radius, you reach the 9.8, and then it becomes constant. And then you go like this. This is how a real Earth works. Like for a good amount
Well,
of
not
time.
exactly real Earth, but yeah, most.
I mean, to two significant
To
digits.
some, yeah, to some approximation, yeah.
Yeah, to almost two significant digits. That's how it is. Right? There is a small variation here. It increases and dips. So, but within two significant digits, that's a pretty good approximation. And now you can see that in this case, remember, by the time you reached half the radius, there is very little mass there, right? Half of the, like more than half is gone, right? Because it is R cubed. But in this case, there is a good bit of solid chunk still there. So the pull is much stronger at this point. So it speeds you up, right? So this one was 42 minutes. If you do this calculation, a little more work, tedious work. First, you have to go from here to here, then here to here, and then you have to calculate this. So this comes out to be 38 minutes, again, to two significant units. Right, that's I never did this calculation. I modeled this, but I think I never reached this answer. I modeled it and got all the necessary things, but I never really calculated the time. This was a paper that came up in 2014, I think, something 2014, I suppose. Let me check. I think I wrote it down somewhere. No, 2013. So yeah, the archive number for this is so archive 1308 and 1342. So that discusses this in an American Journal of Physics. It was published. So yeah, so good points. Yeah, thanks, Raj. Okay, so it's 1 hour and 15 minutes. I think for a change, we should make it decent. Otherwise, we extending it for 1.5 hours. I think I covered most of what I wanted.
Yeah.
Yeah, good.
Nice.
Very good. Thanks, Bipin. Yeah, thanks for asking.
Thanks, Shajesh.
Yeah. Okay.
Yeah.
Okay.
Yeah,
Good.
maybe you can close the recording.
Oh, I can close the recording now. Yeah, that's the
Thanks.
better way of doing it. And after that, it